So our first speaker, so we sort of mixed the sessions up a little bit. So we now have Peter Orbanz speaking. He's from Columbia University. He does have a past in Cambridge. How long were you working with Zubin Garamani here?
4 years.
4 years in Cambridge. Apparently he can't stay away. So we've managed to make him come back. And today he's going to be talking about subsampling, symmetry, and averaging in networks. So please.
Thanks, Sophia. So if you get the feeling that the talks suddenly pass more quickly now, that's because they're shorter. And I only have half an hour, so I will be shockingly short on detail. Okay. Nevertheless, I decided to put in 2 slides in the beginning on like the bigger picture, which means I can probably not finish in the end, but I figured it's more important. So the workshop is called Graph Limits in Statistics. I gather not everybody here is a statistician. So why are statisticians interested in graph limits? Okay. And I will shamelessly claim here that everybody is interested for the same reason as I am. So the setup we're looking at is we observe something, we observe data that is a graph, and we would like to do statistical analysis on it. So the graph is a single graph, and as we get more data, the graph grows larger. We don't see multiple small graphs. Okay. So the problem for statistics is now, what can we learn from that graph? One thing we might do is what we do usually do in statistics is we define a model. In the simplest case, it's just some set of probability measures on the space on which the observations live. So this would be a set of probability measures on graphs. Yeah. So here each p sub theta is a measure. It's indexed by some parameter theta. And what we call a graph-on model is a case where the theta is a graph limit or a graph-on, and p sub theta is the distribution of a graph that we sample from that graph-on. Okay. So now, if we want to estimate something from a single graph, that is difficult because what we usually would do in basic statistics is we take multiple observations, multiple realizations of a random variable, and then we average over those. But now we only get a single realization of that random variable. Yeah? So then we have to ask, can we do something? Can we do anything? And what we would like to have, here I wrote up a list of desiderata here, and they get increasingly stronger. So suppose we have our modeling assumption is we have defined some model. Now we observe some infinitely large graphs, however we do that, right? And we assume that that graph is sampled from one element of this model, but we don't know which one, some undisclosed element of this model. Now, first of all, we should be able to determine that distribution from a single realization of p within the model. Yeah. Second of all, we don't actually, so this graph, if we sample that from a graph-on, the entire graph, the entire realization, that would be an infinitely large graph, right? We're not going to actually observe an infinitely large graph. We're going to observe something finite that we assume is part of that infinitely large graph. So, in fact, our sample size here in statistical terms is less than 1. Okay? So we would also like to estimate p, or in some sense, the estimate of p should converge as this graph gets larger. Okay? So you need some notion of approximation. And then ideally we would also like how quickly it converges, right? And then if we want to have something even stronger, it would be some non-asymptotic result which says how close we are in probability according to some, and gives some probability how close we are for a finite n. Yeah? So typically you need more assumptions as you go down this list. Okay? So in the graph-on case, and that is why we like why graph limits are interesting, this is actually possible. Yeah? In general, we cannot hope that that is possible, but it turns out unexpectedly, if we use graph limit models, that's actually possible. So here, say these two are 2 graph limits, okay? These 2 functions here. So measurable function, symmetric measurable function on the unit square. And now here, PW and PW prime are the distributions on graphs they define. If these 2 graphs are not equivalent, right? So if they define 2 different distributions, then these 2 distributions actually have disjoint support. So, and if it seems impossible to do something like estimating a distribution from a single realization of a random variable within a model, Well, if they have disjoint support, then that's actually possible, right? If they have disjoint support, then you can just, in principle, a single realization completely determines which of the metals, which of the distributions it came from. Okay, so and then as for convergence, that is also true. So Olaf Kallenberg proved in 1999 that if you take this checkerboard function here, which is a graphon that you construct from a finite graph, right? So basically you take the adjacency matrix here. I took the adjacency matrix of a graph of size 10 that I had sampled from Laszlo Loba's favorite graphon. And then I increase the size of that graph, so I sample more vertices, and each time I plot the adjacency matrix as a checkerboard function, right? This function converges to this thing in a sense that you can make precise. And in particular, if you look at empirical averages, so if you take some bounded measurable function, or bounded continuous function if you want, and integrate it against this function, then that converges to the integral under the distribution defined by this, or the integral under the distribution defined by sampling from this function, an infinite graph from this function, gives you, converges to the expectation under the distribution defined by sampling from this. Yeah? So you have a notion of weak convergence. Yeah? So in statistical terms, that is a law of large numbers. Okay. So in my interest, I'm particularly interested in this from the point of view of symmetry. And why is symmetry interesting? Because it basically tells us how to do inference from a single sample, in which case it is possible. Yeah, so if you have some, by symmetry, what I mean, if I have some probability measure, and I know that it's invariant under some measurable action of a countable group, okay? Then I know that I get an integral decomposition like this, where I have a fixed set of probability measures here that I call ERG because they're called ergodic measures. And then my probability measure that I'm looking at, my invariant measure, is a convex combination of these ergodic measures. Yeah? So that's a classic ergodic decomposition theorem for countable groups. And here's my cartoon interpretation of this in the case where the set just has 3 measures. I mean, of course, imagine the set to be infinite, right? But the closest thing to that I can draw is a triangle. I generally like triangles. I really like simple things. So here you have the ergodic measures as the corner points. Okay, so think of each point in the set as a probability measure. These points here at the corners are these ergodic measures, and the entire content of the triangle are all invariant measures. Yeah? So if you have something like invariance under the symmetric group acting on the vertex set of a graph, so a vertex exchangeable graph, then the set of probability measures that satisfies this invariance is some convex combinations of ergodic measures, and the ergodic measures in that case are exactly the ones defined by graphons. Okay, so each graphon indexes, or each equivalence class, weak isomorphism class of graphons indexes one of these ergodic measures. Yeah?
Just to understand do these symmetries apply to the infinite graph, or do they also apply to the sampling process by which we see finite pieces?
So they apply to the infinite graph. Whether you can also make them applicable to the sampling process depends on how you define that group. Yeah. So you need to have a notion of the group acting just on part of the graph. And if you have invariance under permutations, so of course you have to specify which exact action you want. So first of all, we take the symmetric group, the permutation group, and we let it act on the vertex set of the graph. So in that case, you have a precise notion of what it means to shrink it down to part of the graph. You just permute the vertices of the subgraph, right? But you could have a group that takes one graph, one infinite graph, and replaces it by an entirely different infinite graph. In that case, there is no clear explanation of that.
I understand, but I guess the thing I'd like to know is the following excluded. So let's say that the infinite graph is a bona fide graphon, it's fully exchangeable and all that. But then let's suppose that the finite sample of it that I see is, say, the radius R neighborhood of a randomly chosen.
Oh yeah, I'm coming to that. That's exactly what I'm going to talk about next.
Okay,
yeah.
Good. Thank you.
Yeah. So, so we know that especially in the case where we take this countable group to be the symmetric group acting on some component of a discrete structure, we get an exchangeable random structure. And for those, there are nice representation theorems of this type, like the De Finetti theorem or the theorem in the graphon case, the Aldo-Suber theorem. And this is basically, in the graphon case, this is basically the Aldo-Suber theorem minus the most interesting part. And the most interesting part is the encoding of the distribution as a graphon, right? There's no limit object in here. This measure just sits here, and okay, we don't know how to sample from it, right? Okay, but what it does explain is, so these, in general, for a countable group, these measures here have this property that we can do inference from a single graph because we get disjoint support. Okay. So with a bit of additional work, we can also get convergence results directly out of the symmetry. Okay. So we need more conditions on the group for that, but we can get convergence results out of the symmetry, and we can even get concentration results under some additional conditions. Okay, so then the question is, if I don't want exchangeability, what is a useful notion another useful notion of symmetry for networks? Yeah. So that is one thing, and now here's a completely different thing, namely experimental design, and that is something that people in application think about a lot. Yeah. So if you look at papers written about networks and statistics these days, if you look at the theoretical journal, everybody's talking about block models and graphons. If you look at applied journals, people talk about experimental design instead. Yeah, is my impression. So the problem here is, you ask, how should I sample my graph? As you said, I take a neighborhood of something, right? And I'm going to model the experimental design by a randomized algorithm. Okay, so I'm going to invent an algorithm that randomly subsamples my graph. Okay, and then I ask, what can I learn if I have done that with a specific algorithm? So generally, morally, all the graphs I'm talking about are infinite or very, very large. Yeah? And now here's just an example of an algorithm. So I could just, a very simple way of subsampling my graph is, if I want to get a subgraph of size n, I select n vertices uniformly, and then I take the induced subgraph, right? And then I already have to make design decisions. Do I want to sample with replacement or without replacement, right? But and then another thing that you notice here immediately is that this is not actually applicable to an infinite graph, right? Because then I can't sample uniformly from the vertex set. So you have to make that, what you mean by sampling this way from an infinite graph, you have to make that precise with a limit argument, and then you have to do a bit more work, okay? But let's just not talk about that in half an hour, okay? So if I take this specific subsampling algorithm here, then I see that if I sample a graph this way from some gigantic input graph, the output graph is exchangeable, right? I sample a finite output graph. That distribution of that output graph is certainly invariant under permutations of the vertex set, right? Just because the labels of the vertex set arise by in which order do I discover my vertices, right? And that is exchangeable. So, and it's I mean, it's well known in graph limit theory. I mean, it's actually one way that you can define graph limits, that if you subsample that way, then you basically get graphons as a representation of your of the distribution of an infinitely large sample. Yeah. So this gives me, my point here is, I invent this randomized sampling algorithm, and then I ask under what group of what symmetry group leaves the output of that sampler invariant. And in this case, that's exchangeability, so that's the symmetric group, okay? And the point I would like to make today is that the way we can learn how to analyze the data that comes out of the sampler is by studying that group. We can get a lot of information out of that group. Yeah? Okay, so the thing with this algorithm is it gives us this very nice theory of graphons, this very nice representation, but nobody actually uses that. Yeah? Because if you apply this to the Facebook network, you get something that's empty, right? You can bet on it. So, and the graphs that you find on, I mean, if you look at graph data sets that are available online, you find something like graphs that are sampled like this, for instance, what people call ego networks. Yeah, I call it one neighborhoods, but in network science, I call this ego networks. So you select k vertices uniformly, say, or in some way, and then you report the one neighborhood of each vertex. Yeah? So you select a number of people and look at their friends. Yeah? And something else you could do, for instance, is you could select a vertex uniformly, then start a simple random walk, and then report the path of the random walk, or something like that, right? Okay. So now, if we define a subsampling algorithm, then that induces a notion of symmetry. Yeah? Determining what that notion of symmetry is may not at all be easy. Yeah? And but roughly speaking, the symmetry group is the set of transformations that leaves the sample output invariant, right? And here I'm already glossing over things because typically the group of all transformations that leaves the sampler invariant is too large to be nice. And we want to have a group with nice properties. So you have to, typically, for instance, that group is not countable, or in many cases, and then you need to choose a countable subgroup. Yeah. So, so there are different ways to formalize this idea, and the objective is to get a group that has nice properties. But definitely, if you just imagine a situation, you know that some group leaves the output of your sampler invariant regardless of the input graph. And now you define a model that is supposed to model output of that sampling process. Then you will certainly want your model to also be invariant, right? If that is information you have that the sampler data possesses, then you want your model to take that into account, right? Okay. So we uniformly subsample vertices, and the output graph is exchangeable, and then we get the graph on setup, okay? So if we look at the graph on setup from this perspective, then we see that actually some of the pathologies, so in network modeling, people have noted that graph ones are maybe not actually the best models for many types of network data. Yeah? And one reason is that networks are typically sparse, and the graphs we sample from graph ones are not. Yeah? But that is really just part of the problem. So I try to illustrate that we can learn something about these problems by looking at the sampling algorithms. Basically, these are pathologies of the uniform sampling algorithms that induce these pathologies of the graph. So here is a synthetic graph that is reasonably sparse. And now I subsampled this graph in two ways. One is I selected a vertex and took the two neighborhood. Okay, and I get something like this. So here I sample by following edges. Okay? And then I have subsampled uniformly. Yeah, so the way we would do in the exchangeable setup. And I get something like this. Yeah, and there is, you can probably not see it, but there's actually a single edge down here. Okay? So now if I would take this graph, if somebody samples, if this is my large social network, and somebody generates data by sampling from the social network like that, crawling the social network somehow, reports that data, and now I analyze it with a graph one model. Okay? Let's say I take the simplest model, just take an Erdős-Rényi graph, so I'm just fitting the edge density of this. Then my model thinks the graph looks like this. I sampled this from an Erdős-Rényi graph fitted to this, right? Just because there are way too many edges here. For the subsample to look like somewhat like this, this graph indeed would have to look like this if I have actually uniformly subsampled it, right? Okay, so you really can't fault the model. Yeah? Okay, but this is just part of the problem. So what you could now do is you could say, okay, I sparsify this graph, right? I just randomly delete edges or something like that. But so here I took a graph and subsampled it uniformly. This is actually real-world proteomics data. I just subsampled a 40-edge graph, a 40-vertex graph here uniformly, right? And so if you want to analyze, if you assume your input graph looks like this, okay? Think of the subsample as a summary of the information in the input graph that you think is important, right? You take a very large input graph, you subsample it. You'd want to try to extract information that you think is important, yeah? So if you believe that the information that is important for you in this graph is well summarized by something like this, then a graph one model is a good idea, okay? But maybe for many purposes, this is actually not a good summary of this graph. Yeah? So it's about much more. The problem here is much deeper than just the problem that the graph is too dense if I sample it from a graph one. Yeah? It's a structural problem. Okay.
The input graph is connected.
Yeah. So I mean, if you if you sample from a graphon, then the edges are conditionally independent given the marks of the vertex set, basically, right? And this conditional independence is just gonna, it just shreds the structure of this graph, right? You're never gonna see a structure like this long elongated chain here or something, right? Okay. So, and now I don't have a lot of time left. So I just want to show you a quick example of how I can tweak an algorithm, and then 2 examples of results we can get out of analyzing this through symmetry, okay? So what I did here is, so roughly speaking, the uniform subsampling is nice because it makes things so simple, right? So the uniform sampling algorithm, the point is not really that it samples uniformly from the vertex set. What's really important is that it completely ignores where the edges are when it selects vertices, okay? The edge set does not in any way determine which vertices are selected. The edges are reported in the end, but they are not included in the selection. If I follow edges, that's completely different. So how my sampler behaves in selecting vertices depends on the specific graph, right? And that makes the analysis in general much harder, okay? So many of the algorithms that I would like to analyze, I don't actually know how to analyze because I just lack the mathematical muscle for that, okay? So one thing that I can do is, here I picked an algorithm that is almost the uniform subsampling algorithm, and I tweaked it just a little bit. I changed the uniform distribution on the vertex set to the degree bias distribution. So I select each vertex proportionally to the number of edges attached to it, okay? And that changes the properties of the algorithm or of the output drastically, yeah?
It's like selecting a random edge, for example.
It's like collecting a random, uniformly random end of an edge. Yeah. So you sever the edges, and it doesn't matter where they go. It just matters how many there are. And so that means you include a little bit of edge information, but not a lot, right? You're not actually following the edges. And so, for instance, if you that algorithm can resolve sparse graphs, right? So a uniformly subsampling from the vertex set will not resolve a sparse graph. If a sparse graph grows larger and larger, you will get something empty eventually, right? In this case here, here's an example of a graph this can resolve. So you construct a graph that has 2 special vertices, these 2 here, and now you keep adding vertices, and you always connect each of them to these 2, right? And just imagine I do this infinitely often, right? So I may turn this into an infinite graph step by step. So if I sample with this algorithm from this graph, right? Or if I sample with it with a uniform subsampling algorithm, then if we again forget for the moment that we can't actually uniformly sample from the infinite graph, if we would uniformly sample from that, then we will always pick one of these vertices here, right? These 2 just get mass 0 in the limit. We never see one of them. But if we sample in the degree biased way, then each of these has mass 2.5, right? And as soon as we have seen one of these 2, the graph is connected. Whereas if we don't see one of these 2, then the graph remains empty. Yeah? And this graph is very sparse. Yeah? So this algorithm actually can resolve sparse graphs. And I do, in this particular case, I get something that looks a little bit like a graphon representation, but you sample from it in a different way. And because I don't have a lot of time, I'm gonna skip how you actually sample from it. I just want to mention that I don't think we get these kind of nice summary representations like graphon in the general case. Yeah, I don't think we can expect that. Okay, but what I'm really interested in is laws of large numbers, and that involves some notion of averaging. And it turns out that the way we have to average within a single graph, if we just have one graph or part of a graph, that is determined by the group. Okay, so here, let's say we have some set M, which is some finite set of mappings that take graphs to graphs for the moment. Okay, just some set of mappings, and it's finite. And now I define this quantity here, which takes a graph, and then it applies this mapping, each of the mappings in my set to the graph, so I get a bunch of replacement graphs. And then I take an average over those, or rather over point masses at these points. So this is a probability measure. Okay? And think of this as something like an empirical measure. Yeah? So, and now if my, if A here is the symmetry group of a graph, and I said before I want this group to be countable. It shouldn't be too small. If I want nice properties, then it shouldn't be too large. So it should be countably infinite. It should not, finite is too small, uncountable is too large. Yeah? So I have a countable group here. I cannot actually compute this average if the group is countably infinite, right? It only works for a finite group. But it turns out if this group is reasonably nice, and then there is it contains a sequence of finite sets of growing size that approximate it. Yeah? In the sense that if I compute this here for my first set, and then this average over all elements in the second set, this average all elements in the third set, always for a single graph, right? I get a sequence like this, and if I input the output of my sampler, okay, so I draw an infinitely large sample from my graph, yeah, infinite for the moment. I plug that in here. I apply these transformations and average over them. That actually converges to the expected value of some function that I apply it to. Okay, so this is like a plug-in estimate. But I'm not averaging over repeated observations. I'm averaging over surrogate observations that I get by applying elements of the group. Yeah. So this is like an ergodic theorem, but not over time, but I mean for group actions, right? And I had to learn a lot of ergodic theory to get these results, and I think it's absolutely stunning how powerful their tools have become in ergodic theory. It's absolutely stunning. Okay, so averaging within the way that, or a way that we can explain averaging within a single sample is we identify a nice group that leaves the output of the algorithm invariant. Then we approximate the group in this way by these growing sets, which we can do if certain conditions hold. And then sample averages are averages over these sets, right? And I mean, surprisingly to me, the conditions are purely conditions on this group. Not on the space it acts on, not on the action, as long as the action is measurable, only on the group. Yeah? Even certain constants that show up in proofs depend only on the group. Yeah? Okay, so, and then if you add more conditions, you can even get something like a central limit theorem. Yeah? So if the group is now not just nice, but very nice, and a certain moment condition holds, then you get the same but with asymptotic normality. Yeah. And I spelled out the moment condition here, not because I expect anybody to actually parse this, but only because I mean, I'm sure some people here are will look at this and immediately recognize it, because so basically what we have here is increments and conditional variances of what? Well, if you think of this average here, this is a real valued function that we're averaging. So the average is a number. So I have if you forget about all the graphs and the sampling and everything, what I get is really a sequence of real random numbers that are indexed by n, right? So it's a discrete time stochastic process. And we've known for about 40 years or so that the relevant conditions for central limit theorems and discrete time stochastic processes are moment conditions formulated in terms of conditional variances, right? And these are exactly the type of conditions that you see for these central limit theorems, right? What I'm working on with a student right now is these conditions are ugly because they are formulated in terms of the output of the average. So can we translate them back into conditions on the group and the function? And we can do that in for certain groups. That I mean, for a class of group that includes the symmetric group. So one thing that I'm very happy with is we know, for instance, that we can get, as a special case, we can get Hans Bühlmann's central limit theorem for exchangeable sequences. Yeah? So Hans Bühlmann, father of Peter Bühlmann. And I believe, so Peter Bickel has proven a few years ago, has proven an asymptotic normality result for certain estimators in graphon models. And we haven't, I'm sure it's in here somehow, but we haven't actually checked whether we get the same conditions or whether they're slightly different. Yeah. Okay, So, and I think my time is up, so I will just stop here. Thank you very much.
So, I mean, you went through a bunch of different sampling schemes. Have you computed what the variances are in all these cases, or is it okay?
No.
So, like, how hard is that?
Yeah. No. I mean, you have to. If you can even get to the variances, yeah, that's great, right?
You gotta,
I mean,
you gotta invariant.
I mean, the first thing you really have to worry about is how large is that group and what properties does it have. I don't know if we would find that one of these samplers, I mean, some sampling scheme might be really convenient, but the group might be way too small, right, or way too large and too constraining to do anything with it. Whether there is some other way of doing it, whether there are alternatives, I don't know. This is the only way I know of doing it. Yeah, but no, I mean, no.
Have you done it for anything other than the exchangeable graph?
Yeah, so I can do it for the case with the degree bias, in the degree bias case, for instance.
Okay.
Yeah.
But for no edge follower.
So yeah, I actually think that we might be able to do something in the case where you constrain your input graph to even as it grows to have finite degrees, and then do simple random walk on the input graph at a randomly started point. In that case, I mean, we probably need some. We will need some more conditions on that graph, but I think you might be able to do something. Yeah.
Yes, you mentioned the case of a real network like Facebook. How do you plan to apply this kind of algorithm to sample Facebook?
Yeah. So I can tell you that I've been talking to somebody in one of the large social network companies, and they are thinking about how they can subsample their graphs. Yeah? And I know that one thing that they are doing is so one thing is they select vertices deterministically, that like 10,000 vertices or something with the largest degree, and all their neighbors. Another thing that they're doing is they just subsampling edges uniformly. And they've already noticed that that is nice because it gives them unbiased estimators, which is basically what I'm saying here, right? But they have no idea what the implications really are, right? And it's also, I think the way they can sample is also constrained by how the database is set up, right? I mean, these graphs have like 2 billion vertices or something. You can't just apply any sampling algorithm. It really is constrained by how the graph sits in the database. Yeah. But I think, so I'm sure that, again, in the case where you sample edges uniformly, you'll be golden. Yeah? Everything will be very simple. Yeah.
I just missed your point on, you showed a slide where you had you had a graph, and then you showed that if you subsampled from it in various ways, and reconstructed it using a model, then you get something that looks very unlike the graph. So I mean, just wanted to ask, so what's the point of using an Erdős-Rényi there? For example, you could imagine doing a link tracing design and then using an ergom with finite exchangeability, and it would recreate many of the features that you have in the actual graph.
Yeah, no, this here is just to throw a graph on under a bus.
Right, okay.
Yeah. Okay, and this is, I mean, if I just want to fit the edge density here, then I just take a graph and that has only the edge density as a sufficient statistic, graph and model, right? So my point here is really that you can see in which cases, so throwing graph on under a bus is way too general. So in which cases you can see very clearly in which cases a Graphon model is going to be misspecified by looking at the algorithm. That is the point here. If uniform subsampling looks like a good idea, then a Graphon model is going to be a good idea. Otherwise, it is. Yeah.
So one more quick question before we all get caffeine. We'll take one more. Someone have their hand up that changed their mind. Okay. In that case, I suggest we go and get our coffee, because our coffee break is now 25 minutes. So let's thank Peter again.